Hi guys, my name's Carl Van Berendonk. I'm one of the principal engineers at Kudo Controls, and we're Australia's largest vehicle integrator. We write control software for vehicles. A lot of people have been asking me about Donut Labs and their breakthrough solid state battery. I'm not going to tell you what to think, but the whole purpose of this video is, thanks to VTT Labs, some information has been released about the battery, so you can actually calculate yourself and answer this question. Is it good or not? So in order to answer that question, the first thing that we're going to look at, and we're going to use a bit of maths to do this, is what makes a good battery? What we're talking about, first of all, is the battery efficient? And the reason that's important is because a battery that is inefficient dissipates a lot of heat when you discharge it, and that heat is what accelerates degradation and causes battery dendrite formation. And dendrite formation leads into the next thing, which is cycle life. And so if a battery is good, it has a high efficiency and it has a high cycle life. And the cycle life is important because higher cycle life basically means the battery lasts longer. So how do we measure efficiency? Well, you know that if you discharge a battery, the battery seems to have less energy inside. And that's because the battery itself dissipates some energy. So we know using the first law of thermodynamics, which is sometimes called the conservation of energy law, that the energy inside the battery is neither created nor destroyed, which means that the total energy inside the battery, you have the energy that's dissipated in the load, or in the case of an electric vehicle, it's things like the motor, the aircon, etc. And you have the energy that's actually dissipated in the battery itself. And so the energy that's dissipated in the battery itself is the inefficient portion of the battery. If you're a battery expert and you're watching this, don't cringe. I'm going to simplify a whole bunch of stuff, but we're only talking about steady state today, so just keep that in mind. Now, in an electric vehicle, this is what the battery circuit looks like. You have got your electric motor, and we're going to call this the load, right? And the electric motor is connected, and this is a very simplified diagram, to the what's called the res. And inside the res, there is a whole bunch of batteries. But for this diagram, we're just going to say that there is one battery in the res. So in a normal electric vehicle, there's loads of batteries in series. But for the case of this, we're just going to say there's just one battery in here, because that's how VTT did their testing. Now, I'm going to put a discharge curve for a battery on screen so you can see what they look like. The general idea is the more you load a battery, the more the V across the load decreases, which means even though current increases, the total power increases at a lesser rate. When this effect is mild, the battery is very efficient. But when this effect is a lot, then the battery is increasingly less efficient, right? And you have the extreme case, which is when you short a battery together, and to illustrate the point, a good battery would destroy the wire that shorts itself together, and a bad battery would just destroy itself because it would be very inefficient in that case. How do you calculate the efficiency? So the efficiency is given by this equation. It's given by, got my red pen, N equals P load on P total. And we say that P total is a P load plus the P dissipated in the battery. And so when we're talking about P load, P total, P about all of that, right? So the P dissipated in the battery is this one, and the P load is this one. And we can actually figure out what these different components are from the VTT data. So because the VTT Labs test data have a voltage sensor and a current sensor in the circuit, they've given us this current sensor here, which is I. And so the current in the entire circuit, electronics law, the current is the same through the whole circuit. So we know I bat and we know I load. They've also given us V load. So all of their graphs are actually V load, they're not V bat. So they're taken here using a probe, which is connected at these points. And this is V load between this point here and this point here. So how can we figure out, if we want to know what the P bat and the P load is. How can we figure that out? Well, since we know the current is the same through all the circuit and we know V load, it's really easy to figure out P load. P load is actually using, we can use P equals VI, so we just go P load equals I in the circuit times V load, right? But what we don't know is we don't know V bat, and V bat is the voltage measurement. It's basically if we were to put a voltmeter inside the battery here and measure the voltage across the part of the battery that's dissipating the heat, because there's a little resistor in here, and this is what we call the DC IR of the battery, or the DC resistance. Now, we don't know this, which is V bat, right? So we can't use this equation to calculate, at the moment, the power dissipated from the battery, P bat. But we can use this equation, P equals I squared R, because we can figure out R later, and I'll show you how to do that. And I is the same throughout the circuit, so we know it. So we can say I squared times the R DC of the bat, right? Cool, so we have everything we need to calculate the efficiency. We've got the P load, we've got the P bat. Let's go through this. Okay, this is going to get a little bit hairy, but it'll work out in the end, trust me. So we want to calculate the efficiency of our battery, and so we have this equation. We know that the P total equals the P load, and that's our, like, say, motor load, for example, so some might be like 100 kilowatts, right? Plus the power that's dissipated in the battery, right? And we can rearrange this whole thing. We want to say that P load is actually equal to the P total minus the P battery, right? Now, this gives us the equation, P total, which is I times VOC, which is the open circuit voltage. So that's the voltage when the battery is unloaded, minus the I squared RDC of the battery, right? Okay, so if we rearrange this a little bit, then we basically, so we end up with P load over here. We're going to bring it all to the left-hand side. We end up with a positive I squared R DC bat, and we end up with a negative I times VOC, right, equals 0. And this should now remind you of quadratic equation form. So any quadratic equation is going to look like this. And you can see in here that X is going to be I. So VOC is going to be B, and RDC bat is going to be A, and P load is going to be C. Do you see how that works? So when we sub this whole thing into the quadratic equation, I'll make some room up here. We're going to end up with I actual equals VOC plus minus square root of VOC squared, and that's going to be minus 4 DC bat P load, and that's going to be all on 2 times RDC bat. And this tells us how much current is actually required to get a given P load given a given RDC bat. So RDC bat is going to be a property of our battery, and if RDC bat is very low, the battery is awesome, and if RDC bat is not low, if it's very high, basically the battery's rubbish. Cool. So a interesting property of this equation is it actually blows up when the square root term goes below 0. So if this part here is smaller than 0, then that's basically the short circuit condition for the battery. So that is the maximum, in essence, that limits the power level that the battery can handle as a system. So what do we do with all this? So you see you've got two graphs here. You've got voltage over time and current over time. And so this is from the test jig. Remember from first principles that V equals IR, right? And so we can rearrange this R equals V on I like this, right? Now, this works for absolute voltage, but we can create a new equation using the same physical properties. We can say that R is actually also V1 minus V2 on I. So basically we can determine the R of a load based on the voltage delta, which is this, that we see in test data. And you can see whenever there is an I change, there is a voltage delta that we can use. This is actually delta I as well, because you have to match, you have to go delta V on delta I. So looking back at the test data, that's what we're going to do. We want to pick part of the test data where we can very easily see the delta V and delta I, and we want the delta I to be relatively large. So what we're going to do is we're going to pick this point right here. So it looks to me like the delta V is about 175 millivolts, and the delta I, so the test equipment has gone from essentially not testing to testing at 24 amps. So the delta I is 24 amps. So that gives us delta V equals 175 millivolts, which is 0.175, and delta I equals 24 amps. And so therefore we can calculate that R DC bat is V on I, which is 0.175 on 24. Got a calculator. It's about 7.3 milliohms. So at 7.3 milliohms, is this battery good? Well, let's calculate the efficiency at 1C. So when people talk about batteries, they talk about Coulomb rates, and 1C is a pretty low Coulomb rate, to be honest. You'd expect that most batteries at 1C would be about 99.9, maybe 99.95% efficient. Let's take a look. So R equals 0.0073, and the actual P load power that we want is going to be the battery nominal voltage, so let's say 3.7, multiplied by the 1C, so that was 24. So we're looking to get out of this about we'll call it 89 watts, right? So we sub all these into the equation and we say, okay, if the VOC is about, let's say it's like, I'm going to say it's 4.12. Let's go with that. The VOC doesn't matter a whole lot here. But we go 4.12 minus square root of 4.12 squared minus 4 times 0.0073 times the P load of 89 watts. And we put this whole thing on 2 times 0.0073. And it's time to use a calculator again. Do it on my computer. So you've got the I actual is 22.5 amps. Now, with the I actual, we can calculate P total. So the P total equals 22.5 times the open circuit voltage, so that's 4.12, and that equals 92.7 watts. So to get 89 watts, we had to spend 92.7 watts, and this gives us a total efficiency of 96% at 1C. So the claim is that at 11C, this battery would perform well. Can we validate that claim? Well, mathematically, what we would do to do that is we'd say, so this was 1C, we'd times this by 11 and say, okay, that's 979 watts. First of all, can this battery handle 979 watts? Let's give it a go. So remember, we have to check our boundary condition. So our VOC squared minus our 4DC bat P load, that has to be greater than 0 for this equation to be valid. Otherwise, this square root is going to blow up. And when this square root blows up, it means that the battery can't handle that load. So we'll just do a quick check. So VOC, that's weird, negative number. Reason for that is the RDC of this battery is not consistent in their test results at all. So if you go by the 1C test, you get an RDC of 0.0073. If you go by the 11C test, you get an RDC of closer to 3 as an approximation, because virtually every measurement I took from their data came out differently. And that can be because of temperature and things like that, but it's not supposed to vary this much. So using 3 milliohms, we'll have to redo the calculation. And okay, look, this battery might actually be able to do this, but let's calculate the efficiency first to know whether this is a good idea or not. And so we get I actual equals 305 amps. The efficiency is 77.7%. Which means that nearly a quarter of the energy at 11C would be dissipated in the battery as heat. Is this very high? Well, in my experience, as you push further across this, you're going to see this efficiency drop extremely rapidly. I wouldn't generally see an electric vehicle battery operating at an efficiency below 90%. So take from that what you will. Now the big question is the Donut Lab battery relatively a good battery if we compare it with a very common lithium cell? And to do this, we're going to compare it to a battery from over 10 years ago now, the Samsung 25R. Now, what are the specifications of the Samsung 25R? Well, it's a cylindrical cell released 2014. And it has a 2.5 amp hour capacity, so it's designed that you use many of them in parallel. And it has a DCIR of 22.15. That's their guarantee. The actual cell tends to have a lower DCIR than that. And so what we have to do is we have to adjust the fact that this is a much smaller battery. So as batteries get larger, the DCIR also decreases. So we have to go, okay, the Donut Labs capacity divided by the 2.5, you get a factor of 9.6. Then we go 22.15 divided by 9.6. And we end up with an adjusted DCIR of 0.23 milliohms. So 0.23 milliohms versus Donut Labs 0.003. What effect does this have on the efficiency of the Samsung 25R if it were used in place of the Donut Labs battery in the 11C test? Well, you would get I actual equals 282 amps, and you would get the efficiency 84.2%. instead of the Donut Labs 77%. So is the Samsung 25R released over 10 years ago a better battery than the Donut Labs battery? The answer is yes. So if you're running a vehicle development program in Australia, so suppose you're designing an electrified trailer, a 4x4, a mobile machine, an electrified ambulance, fire truck, anything like that, there's no better agency you could be talking to in Australia than Kudo Controls, and we're also the cheapest. So I've left my contact details down in this post. Feel free to drop me an email and we should chat.